Right, welcome to today's lesson on circular functions, or what is possibly called trigonometric functions and graphs. What we have in front of you, as you could see here, is a simulation of a wave. This downloadable feature is available from PHET, P-H-E-T simulation, and is really free of charge. As you can see from the wave that's shown in front of you on this computer screen, the wave is vibrating in a certain way. You could also say it's oscillating, but it's tending to have some sort of form. If we were to play around with the amplitude, which as you can see there, you'll be able to notice the wave getting smaller and smaller. I've got it down to 0.3 of a centimeter. And now if I increase it, if I increase the height or the amplitude, the wave gets bigger and bigger. Also notice you're welcome to play with the frequency, which is rated a number of vibrations per certain time period. And you can see there I'm increasing the frequency to a great deal. Currently, at the moment, it's 2.67 hertz or 2.67 cycles per second. And if I were to lower the frequency, you will see there would be less vibrations per time period or per second. If I were to simply put a normal on it, and you will be able to see the particular wave going up and down, sometimes in physics called the slinky spring or oscillating waves. Well, I think we have a good enough picture about that. We're going to now stop that and carry on with the lesson. So what we're looking at is what we call our sinusoidal or circular functions. And these are typically your trigonometric functions. Right, as you've seen from the simple demonstration we just completed, you'll notice something very important. Excuse me, I'll just adjust this quickly. You'll notice something very important about this, and you notice we have an axis, as you can see, a y-axis and an x-axis. And we can borrow a bit from algebra. So what we now have is a wave that starts somewhere. Well, let's say we start with our trigonometric ratios of sine, cos, and later on tan. But today we want to specifically focus on the sine wave. And this particular wave, I'm going to make it a red color. The sine theta wave. Theta refers to any angle we may call it. So, if we start at the bottom here, which is 0, 0, then what would sine 0 be equal to? Now you have a calculator. Mine is a T184 plus. I'll just put it down here so you can have a look at it for a minute. But what you need to do is look up these values on your calculator, and that'll make life far easier. Right, I have my laptop here, which is far quicker and better. So if I were to look up the value of sine 0, sine 0 for this first point here, I would see the answer is equal to 0. Right, so that's 1.0. Now don't forget that your x and y axis will be very different to what you're normally used to in algebra. Because if your domain is in terms of degrees, then we're going to have so many degrees on the x-axis. Don't forget that, because that is your complete domain for your function sine theta. In this particular video, we're only looking at positive values for the x values. Also, the y values, you would notice later on, would be your height or amplitude. Right, let's have a look. Let's look at our next significant value of 90 degrees. So I put 90 there. This graph is obviously not to scale. And I ask the calculator, what is the sine of 90? And that will be 1. Well, let's put 1 up here, more or less. And that'll be my point there. As you can see with a small x there. Right, so that's 90. So my graph would start from 0, go up to sine of 90, which is 1. Right, so we go back down again to 180 degrees. Of course, if you were to do this in radians, you would know that 90 is pi over 2 and 180 degrees is pi. So what is the sine of 180 degrees equal to? Sine 180 back to 0. So sine 180, the value of that y value is in actual fact 0. Alright, let's look at 270 as my next important point. What is the value of sine 270? That'll be negative 1. That's somewhere down here. And don't forget, this is not to scale, but the 1 and the minus 1, you can see they are more or less the same distance apart from 0. And so what I need to do is take my graph and move it down to, that point there. So I have those points there so far. Right. So sine 270 degrees is equal to minus 1. What is my next value? Let's say 360 degrees. My next most important point. You'll notice we are going in intervals of 90 degrees. That's very important. What is the value of sine 360 degrees? That is equal to 0. And again, that point on that particular graph over there. Right color. Now I just want to even this out a little bit. Looks a bit too jaded. Okay. Now that's more or less your sine graph. Notice it starts from 0, has intervals of 90, and so on. And of course we can change the period or the intervals depending on the particular question. What I wanted to bring your attention to is the following. Is that, of course, you all know what a wave looks like and basically where you can apply it to. There are many examples of waves being applied to music, harmonic motion, sound waves in physics, all kinds of situations where they have oscillations or pulsing of different values across certain points, such as frequency and amplitude related. If you were to redo this graph in radians, you would simply have 90 is pi over 2, 180 is pi, 270 is 3 pi over 2, and 360 degrees is 2 pi. So the graph could also be found. And of course you can solve an equation using these trigonometric functions as well. What is more interesting is to look at a further application of these particular graphs to what is the world famous Ferris wheel. I just need to make some space here. That's science theatre. Right. Now how would this apply to circles, sometimes called the unit circle? Well, I'm going to draw an axis for a circle here. I think we can all see that. And we all agree that 0 degrees is down here, at this point over here. So the sine of 0 is actually equal to 0. But what is the sine of 90? Well, the sine of 90 is 1. And so if I were to now start off in a circular motion, I would have my circle go to there. Sine of 90 is 90 degrees up there. And that's equal to 1. What would sine 180 degrees be equal to? It would be equal to, as we just saw earlier on, 0. My graph would then go down there. Oops, not really a circle, is it? Okay. So that's 180 degrees there. Moving further down to 270 degrees. What is the sine of 270 degrees equal to? Well, that must be -1 there. And again, rotating my circle around like that, nicely. Oops. And again, I go back to 360 degrees. I'm rotating my circle again. What is the sine of 360 degrees? Well, that's equal to 0. So you see we have a full circle. So we started off with 0. We are dealing with the sine graph. And we have to find the different values for sine. Those of us who know a bit more trigonometry will realize that the vertical component is the sine value. So when I have the sine of 0, don't forget the vertical component would be your y value in a sense. I would have something like this for x and y. So instead of just 0 on its own for sine 0, I would have 0 and 0 for x. So here I would have, for example, 1 and x is 0. 1 and 0 there. Here I would have 0 and 0 because x is 0 and y is 0. Here I would have 0 and -1. So excuse me, that's 0 and 1 there. My apologies. 0 and 1. X comes first, y comes second. 0 and -1, and back to 0, 0. So this is my typical, what I would like to call Ferris wheel example. Right, and hopefully you have a good understanding of how the sine graph and the cos graph are interrelated. How the sine graph and the Ferris wheel simulation are integrated. Bye-bye.